Welcome back. Up until this point, we talked about sorting algorithm, bubble sort, insertion sort, selection sort, that were called elementary sorts. They were okay, but they had those nested for loops, and most of the time, it was O of n squared, which was a little bit slow. Can we do better? Well, yes we can. We're going to encounter our last big O on our list. O of n log n. Now, in order to understand what O of n log n means, we have to talk about our next sorting algorithm, merge sort and quicksort. You see, unlike bubble sort and insertion sort and selection sort, they use the technique that we've heard of before, divide and conquer. We learned about this when learning about trees. Remember, when looking through a phone book, we open up that book not from the first page, but from the middle page. And we keep breaking up the pages until we find the name we're looking for. And merge sort and quicksort use this concept of divide and conquer and the idea of recursion, which we've talked about, to divide the problem down to do work on each subset and then combining the solutions. Now, we're going to see how this actually works. But I want to remind you that anytime we see something like divide and conquer, it usually gives you a log of n advantage. And as you can see here, it is the last piece of the puzzle, O of n log n, that actually improves, is better than O of n squared. The next couple of sorting algorithms we're going to look at are not going to have nested for loops and have O of n squared. Instead, they're going to have this time complexity, which makes things a lot better and saves companies a lot of time. In order to understand what this means, we have to start off with looking at merge sort. Let's have a look at how it works, and then I'm going to explain what the benefits are. We have the same list as before. We're going to take this list and actually divide it in half. And then we're going to divide each of these subsets into half again. And then we're going to divide those sublists into half again until we have one item. And once we have that divided up, we're going to take the first item and second item and say, hey, which one should I put first? Let's put 5 first and then 6 right after. And notice here how we're building a reverse tree in a sense. Then we look at 3 and 1 and say 1 and 3. So we're getting closer and closer to that root node. We're comparing 8 and 7. 7 comes before 8. 2 and 4. 2 before 4. And now we again combine those lists in that reverse tree, saying 5 and 1, which one comes first? 1 comes first. And then let's compare 5 and 3. 3 comes first, then 5, then 6. Then we look on the right side. We say 7 and 2. 2 comes before 7. What about 7 and 4? 4 becomes before 7. And because we know that 7 and 8 are already sorted, we just place 7 and 8 right next to each other. And then finally, we combine these last two lists into our root node to combine the list and make it sorted. 1 and 2, 3 and 4, 5, and then 6, 7, and 8. And we have our sorted list. Now, that looked extremely complicated. A lot more complicated than the other sorting algorithms, right? Merge sort is one of the most efficient ways you can sort a list of things, and typically is going to perform better than most other sorting algorithms. And in terms of complexity, well, it's definitely a lot more complex, isn't it? We're using divide and conquer approach, which should tip you off that it's going to use some sort of recursion. The first part of n log n, that is n, comes from the fact that we're still comparing everything. We have to look at each one of the numbers and compare them in order to sort it. Now, once we divide the list into 1, which finding the middle index of these things are actually O of 1 because it's an easy mathematical operation. Get the length of the list and find the middle. But once we divide the array, we need to sort the items, which is going to take O of n. We have to look at every single item and actually sort them. And we're able to create the list. But unlike bubble sort, for example, although we have to compare everything at least once, we don't have to compare everything to everything like we did with bubble sort. All we have to do is compare their local lists to each other. Remember, with something like bubble sort or insertion sort, once we went through the list once, we then compared the next item to the rest of the list. Merge sort is also helpful because it's what we call stable, which just means that if you have equivalent elements, that is, let's say 6 and 6, or a name that is the same, it will keep the original order in the array. And this can sometimes be important depending on the type of data. Let's have a look at its big O. We see that merge sort has O of n log n, with a space complexity of O of n. Unlike bubble sort, insertion sort, and selection sort, we have a bit of a bigger space complexity because we have to hold on to that divided up list in memory. So that is one downside of merge sort. But we've now managed to make our sorting algorithm a lot faster. Now, how do we implement merge sort? I have here for you an exercise. I want to warn you, this is really difficult. Merge sort is really hard to implement and wrap your mind around. If you don't feel comfortable with recursion, it's going to be a little bit tough. Keep in mind that I'm showing you here how to do it just for your own interest. But most likely in an interview, you're never going to be asked to implement your own merge sort. You're just going to be asked maybe how it's implemented. And I've created a little skeleton to help you out here. We have the merge sort that is going to have a function that takes an array. We have the base case because we're going to use recursion here, saying that when array length is 1, remember, there's only one item in the list. That is, when each one of this is up at the top in its own list, we're going to just return the array. Now, in here, we're going to return, and we're going to merge sort the left-hand side and the right-hand side. And we're going to use this function, merge, that is going to merge the left-hand and the right-hand side. So the first step is for you to split the array down the middle in the left-hand and right-hand side in here. Then run it with the merge sort algorithm. And in the merge function, I want you to actually do the comparison. I don't expect you to get this right away. There's very few people that can do this off of the top of their head. But see if you can use all your resources available, our Discord community, or even Google, to figure out how to create your own merge sort algorithm. And I'll see you in the solution video. Bye-bye.